Welcome to this lecture on linear programming and applications. Today, we are diving into a fascinating topic, linear programming in games. Imagine you are a penalty kicker in soccer. If you always kick to the same side, the goalie will easily figure it out and block your shot. To win, you must mix up your strategy unpredictably. But what is the exact mathematically perfect mix of left and right kicks? That is exactly what we will learn to calculate today. We will see how to turn a psychological guessing game into a rigorous mathematical optimization problem. Let us get started. Now that we understand the basic premise, let us look at the core concepts of game theory. Why does this matter? Because in highly competitive scenarios, being predictable means losing. In a zero-sum game, whatever player 1 wins, player 2 loses. Often, there is no single obvious best move for both players, a situation we call lacking a saddle point. When this happens, players must use mixed strategies. This means instead of picking one move every time, you assign a specific, calculated probability to each available move. Our goal is to maximize our guaranteed minimum score, no matter what our opponent decides to do. Building on the idea of mixed strategies, let us look at how we guarantee that minimum score. Conceptually, we must ensure that our average payoff is at least a certain value, no matter which column the opponent plays. In this formula, A sub ij represents the payoff matrix entries. The variable x sub I is the probability that player 1 chooses a specific row. The variable v is the value of the game, which is the absolute minimum guaranteed expected payoff. If player 1 increases the probability of a high payoff row, the expected value rises, provided the opponent does not perfectly counter it. This inequality we just saw leads us to an important mathematical trick. To convert our game into a standard linear programming format, we divide every term by the game value v. This creates a new variable, capital X sub I. Because the original probabilities must add up to 1, the sum of our new variables equals 1 divided by v. We call this sum z. Player 1 wants to make the game value v as large as possible. Mathematically, making a positive number as large as possible is the exact same thing as making its reciprocal as small as possible. Therefore, our objective becomes minimizing z. Before we move on, let us see this with a concrete example. We are given a 2x2 game where row 1 gives payoffs of 4 and 1 and row 2 gives payoffs of 2 and 3. We are asked to find the optimal mix strategy for player 1. We choose this algebraic approach because there is no saddle point. Our first step is to define our variables. Let x sub 1 and x sub 2 be the fractions of the time player 1 chooses row 1 and row 2. Since these are probabilities, their sum must equal exactly 1. Continuing with our setup, we now write the expected payoff inequalities for each of player 2's columns. If player 2 plays column 1, player 1's expected score is 4 times x sub 1 plus 2 times x sub 2. This must be at least v. We write a similar rule for column 2. To find the absolute perfect strategy, we assume these two worst-case scenarios are perfectly balanced and equal to each other. We do this because if one side were larger, player 2 would simply always play the column that gives player 1 the smaller amount. Now that we have our balanced equation, we need to solve it. We know from our very first step that x sub 2 is exactly equal to 1 minus x sub 1. We substitute this expression into our balanced equation, wherever x sub 2 used to be. This is a crucial step because it transforms an equation with two unknown variables into an equation with only one unknown variable. Next, we distribute the numbers and combine the similar terms on both the left and the right sides. This simplifies our complex equation down to 2x sub 1 plus 2 equals negative 2x sub 1 plus 3. We are now ready to find our final probabilities. By moving all variables to the left and numbers to the right, we get 4x sub 1 equals 1. Dividing by 4 gives us x sub 1 equals 0.25. Subtracting this from 1 gives us x sub 2 equals 0.75. Finally, we plug these optimal probabilities back into our expected payoff equation to find the game value v. The arithmetic gives us exactly 2.5. Physically, this means player 1 is mathematically guaranteed to win an average of 2.5 points per game over the long run, regardless of what player 2 does. So, we have successfully solved the game for player 1. This brings us to player 2's perspective. Why do we need to look at the other side? Because game theory is symmetric. Player 2's goal is the exact opposite of player 1's goal. Player 2 wants to minimize their maximum possible loss. This mirror image perspective creates what we call the dual linear programming problem. Just like player 1, player 2 must choose probabilities, which we will call y sub 1 and y sub 2, for choosing column 1 and column 2. These probabilities must also add up to exactly 100%. Let us formalize player 2's worst case scenario. Conceptually, player 2 wants to ensure that if player 1 strictly plays row 1, the amount player 2 loses is capped. In this formula, y sub 1 and y sub 2 are the column probabilities. The numbers 4 and 1 come directly from the first row of our payoff matrix. The inequality states that this expected loss must be less than or equal to the game value v. If player 2 increases the probability of a column with a lower payoff for player 1, their expected loss decreases, keeping them safer. Just as we did for player 1, we transform this into a standard linear programming format. We divide the original inequality by the game value v, creating new variables capital Y sub 1 and capital Y sub 2. The sum of these new variables is called w, which equals 1 divided by v. Because player 2 wants to minimize the game value v, this is mathematically identical to maximizing its reciprocal, w. Notice that player 2's problem involves maximizing an objective with less than or equal to constraints. This is the exact mathematical mirror image of player 1's minimization problem. Now that we have formulated both sides, let us look at this diagram summarizing the entire transformation. On the left, you see the standard payoff matrix representing the psychological guessing game between player 1 and player 2. The arrow in the middle represents our algebraic transformation. On the right, you see the rigorous optimization problems. The top shows the primal LP for player 1, which minimizes Z subject to greater than or equal to constraints. The bottom shows the dual LP for player 2, which maximizes W subject to less than or equal to constraints. This beautiful mathematical symmetry proves that both players, if playing perfectly, will ultimately reach the exact same perfectly balanced game value. Seeing this symmetry leads us to ask, why does this mathematical translation matter in the real world? Because without linear programming, solving games with more than 2 choices is nearly impossible for a human to do by hand. By converting games into LP models, computers can instantly find optimal strategies for incredibly complex, multi-layered scenarios. This exact math is used in military strategy to allocate troops unpredictably. It is used in cybersecurity to randomize defense mechanisms against hackers, and in financial markets to balance investment portfolios against unpredictable market shifts. We replace dangerous guessing with mathematically guaranteed optimal decisions. We have covered a lot of ground today, so let us reinforce the most important ideas. First, when a zero-sum game lacks a saddle point, players must use mixed strategies to remain unpredictable. Second, we can translate this into algebra. Player 1's goal to maximize their minimum payoff becomes a primal linear programming minimization problem. Third, player 2's goal to minimize their maximum loss becomes the mirror image dual maximization problem. Finally, solving these models guarantees the absolute best possible outcome. You now understand the complete mathematical foundation of linear programming in games. Excellent work!